The things that I'm going to present today are quite fresh results. They are about Radon-Nikodym type theorems for pseudo-integral multilinear operators and homogeneous polynomial operators, and how the talk will be constructed today. First, I will give main definitions and notations. Also, I will present the classical Radon-Nikodym theorem as a motivation. Then the basic concepts of random measure and pseudo-integral operators will be discussed, and after that I will introduce the main results concerning, as I told, pseudo-integral multilinear operators and pseudo-integral homogeneous polynomials, more precisely Radon-Nikodym type theorems for these classes of operators. Okay, let me start with some notations. This is necessary for understanding. We will denote by these symbols a beautiful mu, and this symbol the sigma finite measure spaces, denote by L0 mu and L0 lambda as the spaces of classes of equivalence of measurable functions. And so let me start with one of the main definitions of the theory of ideal function spaces. A vector subspace of E of L0 is said to be ideal function space whenever, together with each member X, it contains every other measurable function which is majorized by X. Majorized means this equality to be fulfilled. A typical example of the space of this kind is a pair-integrable measurable functions LP spaces. And in the sequel, let me assume that E and F are ideal function spaces over our measurable spaces. These two ones, L0 mu and L0 nu and nu, respectively. In our talk, for simplicity and transparency, speaking of E and F, we can keep in mind the particular case when E is equal to LP on unit interval and F is equal to LQ also in a unit interval. This is, of course, a very special particular case, but it provides an adequate idea of the main approaches and results. Now several definitions. We denote by this symbol the space of all linear operators acting from E to F, and we call a linear operator positive if the image of a positive element is positive. We call it regular if it is representable as a difference of two positive linear operators, and we call linear operator order continuous if T sends each lambda almost everywhere convergent order bounded sequence to mu almost everywhere convergent sequence. Here I present, just to illustrate, I present two examples, but I don't think that it is necessary to stop here on them. You can see them on the slide. I mean the examples of positivity of function, what it means. In the case of kernel function, the operator is positive if the kernel is positive, and in the case of multi-application operator, it is positive if phi is positive also. I just don't stop on them here. So our main motivation here is presented. It is a classical Radon-Nikodym theorem, which states that given a measure space with a sigma finite measure mu and an arbitrary sigma finite measure nu, which is absolutely continuous with respect to mu, then there exists mu measurable function F such that nu is representable as an integral of measure mu, as you can see it here. Oh, sorry. Yeah, as you can see it here. Further, in this context, two functionals are considered, which are integrations with respect to measures mu and nu. Then the Radon-Nikodym theorem can be stated equivalently in terms of these functionals as follows. Psi is absolutely continuous with respect to phi, if and only if there exists an essentially bounded measurable function f, such that psi is a composition of phi with a multiplication by f. Here, psi is absolutely continuous with respect to phi, means that so are the corresponding measures mu and nu. This notation, yeah, absolutely continuous with respect to phi. This relation can be defined in terms of psi and phi even if they are linear operators acting from E to F. But we will omit this definition for simplicity and transparency. Instead, we can keep in mind that this relation is something like absolutely continuity. And it turned out that this functional version of classical Radon-Nikodym theorem can be extended to positive operators. It was obtained by Schep and Luxembourg in 1978, and it says that let S and T be linear operators acting from E to F, with T positive, also order continuous and interval preserving these additional properties called Magaram. That the operator T is Magaram operator. So if T is so, and S is absolutely continuous with respect to T, then there exists a multiplicator here, F, multiplicator F on L0 mu, such that this representation holds. Here, without going into details, the formula which is read like S is absolutely continuous with respect to T means that there is a sequence of all operators such that the following such that two conditions are fulfilled. First is that each member of the sequence is dominated by a scalar multiple of T, and the second is that the sequence itself converges pointwise to S almost everywhere. So we are continuing to define the main concepts, and here I will speak about the random measure notion. First, let me say that the concept of a random measure, also which is known as transition probability, came from the theory of Markov processes, where the first example of a pseudo-integral operator also appeared. A family of measures, which is a random measure, used in the theory of Markov processes for determining the distribution at future instance from known states at previous times. Sometimes the term Markov kernel is also used instead of the random measure term. So the definition. A random measure is a real valued function in two variables, such that the first variable runs over the underlying set A, and the second one runs over sigma algebra B beautiful. And two conditions are fulfilled. Firstly, if we fix the value of the second variable, then we get a measurable function in first variable. And secondly, if we fix the value of the first variable, then we get a positive sigma additive measure nu s. Here it is, nu s on B. Speaking about random measure nu, it is usually we identify it with the family of measures nu s. And here nu s acts from beautiful to, no, it's real valued. So this we will skip very quickly. The construction of the product of two measure spaces is well known. Similar construction is possible if one of the measures is replaced by a random measure, as I told, with a family of measures, yeah, which is identified with a random measure. And details are technical, so I only fix that along with the classical product measure mu odd times lambda, we get another measure nu hat. We denote it by nu hat on the product sigma algebra, which is the product of the measure mu and with the random measure nu. Here we can see the notation. So, as before, E and F are ideal function spaces, and let me remind you once again that if you wish, you can take LP and LQ instead of E and F. Here is the definition of the pseudo-integral linear operator. A positive operator T is said to be generated by a random measure nu or is called pseudo-integral if for every x of E this representation holds. We denote by this symbol the subspace of the ordered space consisting of all differences T1 minus T2, where these T are positive pseudo-integral operators acting from E to F, and of course members of this space are called pseudo-integral operators. We now consider two classes of pseudo-integral operators as examples. The first class consists of classical kernel operators or integral operators. So linear operator T acting from E to F is called a kernel or integral operator if there exists a measurable function k, a measurable function k of two variables such that for all x in E, this representation holds. So it can easily be seen that every kernel operator is pseudo-integral operator. And indeed, very easy calculations show us that it is true. I will not stop on them. And the other example is the weighted shift operators. More precisely, we say that even the sum of weighted shift operators is a pseudo-integral operator. A weighted shift operator, known also as a weighted composition operator, is defined by this formula. You can see it here on the slide. Here it is. And it is defined as a composition followed after multiplication. Composition followed after multiplication. In more details, the composition of a given function x with a fixed measurable mapping phi, which is called shift or change of variables, is first taken, and then the result is multiplied by a fixed measurable function a, which is called weight. So we take the sum of weighted shift operators, and we say that it is also pseudo-integral operator. Again, very simple calculations shows us that this proposition is true. Now I want to say that in 1970s, a remarkable result was obtained while describing the class of pseudo-integral operators as a class of order continuous operators. Recall that an operator is order continuous operator if it sends every sequence convergence almost everywhere into a sequence which converges almost everywhere. Every pseudo-integral operator is evidently order continuous. This is due to Lebesgue-dominated convergence theorem. But the converse is a very non-trivial fact and constitutes the contents of the following theorem. Here it is on the slide. It says that let E and F be ideal function spaces over standard measure spaces B and A. Then every order continuous operator T has this representation. As a special case, when E is equal to F and equal to L infinity can be found in the book by Neviot, Mathematical Foundations of the Calculus of Probability. Pseudo-integral operators were fruitfully applied also by Arason to the study of operator algebras of the Hilbert spaces L2. And in particular, he obtained the result for the case when E is equal to F and equal to L2. The analogous independent proof was found by Source, and Weiss, he obtained the general. He proved the general case. So here are presented. The literature is presented, and now we can formulate the Radon-Nikodym type theorem for linear pseudo-integral operators, which was proved in 2003 by Grobler, group of mathematicians Grobler, Departe, and Rambanet. The result tells us that if T is a pseudo-integral operator with representing random measure nu, and some operator S is absolutely continuous with respect to T, then S is also pseudo-integral operator, and its representing random measure is obtained from nu T by multiplication by the kernel G, which is measurable function of two variables. And here the problem arises that pseudo-integral operators have a number of other interesting problems, properties. So it is natural to try to extend the theory of pseudo-integral operators to some other classes of nonlinear operators. In this talk, I introduce pseudo-integral multilinear operators and pseudo-integral homogeneous polynomials, and as I told before, and prove corresponding Radon-Nikodym type theorems. Now I will recall some definitions regarding multilinear operators. These are those who are linear in each variable, and the multilinear operator acts from the Cartesian product of E1 times En to F, and it is called positive if each collection of positive elements is sent to a positive element. It is called regular if it is representable as a difference of two positive elements. By this symbol, let me not read it, by this symbol we denote the space of all regular and linear operators acting from here to here. And to extend the concept of pseudo-integral representability to multilinear operators, it is necessary to consider the product of a finite number of measure spaces. The latter is a Cartesian product of the carrier sets, which carrier sets with the product sigma algebras and product measures. Here it is, product measure. The multiplication of measures is defined on rectangles. Here they are, as the product of the measures of the sides of rectangles, and then is uniquely extended to the entire product sigma algebra. So Here are some notations also, and now the following definition introduces a class of multilinear pseudo-integral operators. This class has, I want to emphasize, this class has not been studied previously. So we say that a positive and linear operator T is generated or represented by a random measure or is called pseudo-integral if this representation holds. It's quite similar with the linear case, but here we can see the product of functions x1, xn. We also make some notations. By this symbol, we denote the space of all pseudo-integral multilinear operators, which is a subspace of the space of linear regular operators. So this is yeah, and the elements of this set are, of course, called pseudo-integral operators. Now we can formulate the first main result of this talk. This is Radon-Nikodym type theorem for multilinear operators. For multilinear pseudo-integral operators. And the result tells us that if T is a pseudo-integral and linear positive operator with the representing random measure nu T, we denote it by this symbol nu T, and some n-linear operator S is absolutely continuous with respect to T, then S is also a pseudo-integral operator, and its representing measure is obtained from nu T by multiplication by the kernel GS. Which is a measurable function of n+1 variables, and if in addition S lies in the order interval between 0 operator and T, then GS lies between a 0 function and identically 1 function. And the mapping sending each S into corresponding representing kernel GS is a linear isomorphism. So this is the Radon-Nikodym type theorem for multilinear pseudo-integral operators. And to formulate the second main result, let me first give some, again, definitions, but I want to ask how much time I still have.
We're already over time, so if you can wrap it up.
Okay, then I will just. Yeah, okay, I see. I'm sorry, I will be very fast. I will not introduce the definition of a polynomial. I just show it here on the slide. I just want to say I will omit all these slides and will just say that for the class of homogeneous polynomials, we have, these are the ones I will say, which are nonlinear operators, and for this class we also have the Radon-Nikodym type theorem, and it is represented here. I just finish on this way, and this is all, I think.
Thank you very much.